Hi everyone, welcome back. This is going to be our next lecture. We're going to finish up some of the matrix determinant stuff, and then we're going to move on to matrix eigenvalues and eigenvectors, which are one of the most important concepts in linear algebra. They play the same role as like the fundamental theorem of calculus does in fundamental theorem of integral calculus does in integral calculus, in that they capture the overall behavior of linear algebra and matrices. So let's go ahead and get to them. So first, though, let's talk a little bit more about determinants and remind you all of what we learned at the end of the last class. So we talked about these things, these matrix determinants, and we gave you how to compute them for a 1-by-1 matrix, which, so the determinant of a 1-by-1 matrix is just whatever value is in that one block. The determinant of a 2-by-2 matrix is a little bit more complicated. It's this weird AD minus BC thing. So and one way to think about that is you're going down along the main diagonal, so that's a plus, and then you're going up along the other diagonal, and that's a minus. So now, and of course, you should remember that even though this notation looks like absolute values, determinants can be positive or negative. And so you can have a negative determinant, and this corresponds, if you think about determinants as some sort of scaling behavior, they correspond to flipping the whatever object, flipping a unit square, or flipping a unit line. And so, in some ways, the determinants is the sign scaling factor of the area or the volume or the length, depending on whether you're in 1D, 2D, or 3D. Well, length for 1D, area for 2D, and volume for 3D. And of course, the negative sign means a flip somehow. So, as we discussed, matrices can correspond to these transformations. And this is measuring how it scales the area or volume of the transformation of a unit square. And so, this also means that it makes sense that when you scale the area down to 0, it's no longer invertible. And so one of the really important properties of the determinant is that lets you know whether or not a matrix is invertible without having to go through the entire process of Gaussian elimination. But we've only defined the determinant so far for 1-by-1 matrices and 2-by-2 matrices. So now we just got a question from Ken here in chat. Are we responsible to know determinants for 3D? And the answer is yes, and I will be getting to that now. So I'm going to actually give you the determinant in any dimension. So this is going to teach you how to compute the determinant for any n by n square matrix. So this is the general answer, which is using minors and cofactors. So if we have some matrix A, which is a square matrix, let me give you this in the 3-by-3 case, just as an example. So I'm going to label the coefficients A11, A12, A13, A22, A21, A22, A23, A31, A32, A33. That's pretty standard notation for the different entries of a square matrix. This is a matrix, not a determinant yet. Then we can define something called the minor of a matrix. So it's the determinant of the matrix when you've removed the ith row and the jth column. So let's see, let me put that here. So the M11 minor is going to be where you've taken the first row and first column and removed those. So you've removed that and you removed that, and so you're just left with this box here. And so then that leaves you with this M11 minor is the determinant of A22, A23, A32, A33. And similarly, the M12 minor is going to be equal to A21, A23, A31, and A33. And so on. So we also have an M213 minor, which is going to be, let me write this in a little bit more space actually. Yeah, so let me just write it down here. The M13 minor is going to be A21, A22, A31, A32. And now, once you have a minor, we're also going to define something called a cofactor, which is going to be plus or minus the minor. And this is going to be important for a couple of reasons that will become obvious in a moment. So it's just minus 1 to the I plus j times mi plus j. I'm sorry, mij. So it's just either plus or minus of the minor. And one way to keep track of this is if you draw out a matrix and you put in the checkerboard pattern of pluses and minuses. So I'm going to put in a little plus here, minus, plus, minus, plus, minus, plus, minus, plus. Then this tells you what minus 1 to the I plus j, that entry is going to be for any of the minors. So for example, the M11 minor, so C11 is going to just be equal to M11. But on the other hand, C12 is going to be equal to minus M12. And C13 is going to be equal to M13 again, because that's the sign of the cofactor. So the cofactor is just the minor with a plus or minus sign. So multiplied by plus or minus 1. So of course, if the minor is negative to begin with, because it's a negative determinant, then the cofactor is going to be positive. So now, once we've defined all this, this gives us a recursive definition of a matrix. Oh, sorry, that overlapped a little bit. But all you're doing is you're taking some row. So for example, you might take the first row, or any column. So you can expand along any row or column. Why do we start with plus for the checkerboard? Because if you look back here, if you look back here, this definition is minus 1 to the I plus j. The first entry is 1, 1, right? 1 plus 1 is 2. So the first entry is minus 1 squared, so it's 1. And so because as you move along this checkerboard, you're increasing the power of minus 1 each time, and so it flips sign each time. And you start with a plus in the upper left. So the important part, so if you go back to the form, the checkerboard is just a way of thinking about it. The important part is the original formula, so minus 1 to the I plus j. But so now you can determine determine the determinant recursively by saying that the determinant of a matrix, the matrix A, is equal to the entries along the first row, so A11, times the cofactors along the first row, C11. So you end up with the matrix A being the determinant of A being equal to A11, since that's the entry in the top left, times your C11, which is just going to be the determinant of A22, A23, A32, A33, and then minus A12 times the determinant A21, A23, A31, A33, because of course that cofactor had a minus sign, plus A13 times the determinant of A21, A22, A31, A32. Okay, and this actually lets you give you the general formula for a 3x3 matrix. So that is A11, A22, A33, no plus sign there. Oh, sorry, I just erased too much there. So this is A22. Okay, A33. And I'm going to have the negative sign down here just to make things a little bit easier. This is A11, A23, and A32. And here, note that you're subtracting A12 times A21 times A33, and you're adding A12, A23, and A31. Here you are adding A13, A21, A32, and subtracting out A13, A22, and A31. Okay, so let's let you compute the determinant of a 3x3 matrix, and note that you can actually expand along any row or column using this formula. So we expanded along the first row, so A11, A12, and A13, and multiplied by the cofactors C11, C12, and C13. But you could have done that along the second row, or the second column, or the third row, or the third column, and you'll get the same response. Proving that these are all entirely equivalent is beyond the scope of this class. And I won't expect you to know the proof, but I do expect you to know how to compute the determinant using a cofactor. For the 3x3 matrix, since you'll be seeing a number of those, it's often useful to just memorize this formula. And there's a relatively easy way to remember this formula. So if you start with a matrix, A11, A12, A13, and A21, A22, A23, and A31, A32, A33. If you start with the matrix, we're going to augment it by putting another copy of the first two columns. So A11, A21, A31, A12, A22, A32. And then for every one of these downward diagonals, they're going to be positive. So these downward diagonals, those are all going to be positive. So plus for downward diagonal. And for all these upward diagonals, minus for upward diagonal. And you can sort of remember this because if you think back to the 1-by-1 matrix, A, B, C, D, that's basically what you were doing as well. So you had a minus sign there, sorry, a plus sign there, and a minus sign for the BC. And you can sort of remember this by looking at, if you just have A11, A12, A13, A21, A22, A23, A31, A2, A33, even without drawing the augmented matrices, you can sort of see this go on. A22, A23, A31, A32, A33. Because you're basically taking all diagonals, including wrapping around. So that's positive, and this is positive, and this is positive. And then you have the negatives, which are the ones that go up. How did you get the augmented matrix? I just took these two columns and I copied them over. So this is just a memory aid. So this is okay. So let's give an example. Yes. By wrapping around, I just mean that when you're writing out this augmented matrix, then you can just look along the diagonals. But sometimes it takes too much time to actually write out the augmented matrix, and so in that case, you can just look to see all different diagonals as you're going down or going up, all different combinations of three things. So if you are familiar with chess, you might think of this as all different combinations where you can place rooks on the chessboard such that they aren't able to capture each other. Let's give an example. These things are a lot easier when you're actually computing them, and rather than just having this really abstract thing. So let me start with a simple example. This is going to be 0, 1. Sorry, let me get my example correct. Don't want to mess that up. Let's say this is 0, 1, and 0, and 2, 1, 3, and 6, 5, 0. Okay, so what's the first thing we're going to do? We're going to do this a couple different ways, just so that we're all clear on how to do this. So the first way we're going to do this is we're going to say that this is going to be equal to, we're going to use the cofactor expansion. So this will always work for any matrix, and if you don't remember this mnemonic, then you can just do the cofactor expansion. So this is, we're going to expand along the first row, okay? So this is going to be 0 times 1, 3, 5, 0 minus 1, because of course we have this plus minus plus minus plus minus plus minus plus, minus 1 times the determinant of 2, 3, 6, 0, because those are all the entries that aren't in the second column or the first row, plus 0 times 2, 1, 6, 5. Sorry, let me put that in red, since I was putting everything else in red. Okay, so that is the cofactor expansion along the first row. You don't have to do it along the first row, but sometimes that's easier. So that's going to be equal to, well, the zeros cancel out, so this is going to be minus 1 times, well, 2 times 0 is times 0 minus 18 which is just equal to 18. Now, let's think about it using the mnemonic. So an alternate way of thinking about it is if we write out the augmented matrix 0, 1, 0, 2, 1, 3, 6, 5, 0, and we copy the first two columns, 0, 2, 6, 1, 1, 5. Well, if you look at all the things that are positive, so this row here, this diagonal there, there's a 0 in there, right? So that's just a 0 entry. This entry here is 18. So we get is equal to 18. This entry has a 0. As we go up, that entry has a 0, that entry has a 0, and that entry also has a 0. And so you get that this is just equal to 18. Okay, is that still too fast? Or please ask me more questions if that is confusing. There will be a couple examples for you to try out in a moment as well. But basically, these are the two different ways of computing the determinant for a 3x3 matrix. And one way is using this memory aid, where you're looking at the diagonals that go down versus the diagonals that go up. The other way of thinking about this is using this cofactor expansion. The cofactor expansion is in some ways more correct, and it's also more generalizable because it works for any size matrix and not just a 3x3. But you'll see 3x3s often enough that it's useful to see it as this going down, going up. The other thing I'll note is that you can also think of this as wrapping around. So if you look at this, let me put this in orange actually. So if you look at each of these things that goes into the augmented matrix, this line here, you could think of it as continuing along to the 6 instead. So the 6, so that's what I mean by wrapping around. Go down, and could you use the going down and going up one for other sized matrices? No, that does not actually work out for rather subtle reasons that will become that I'm not going to go into the proof of in this course. So if you see a 4x4 matrix, you have to use the cofactor expansion. There is a way to generalize this going down and going up, but it involves sign permutations. So if you've taken classes that have taught you about permutation matrices or sign permutations, that's what that makes use of. And which is going down, going up works for 2x2 and 3x3, but doesn't work for any other size matrix. But there was a question about this wrapping around. So this 5 also sort of wraps around here. So you can think of it as this 5 wraps around to this 2 and 5. So and you can do the same thing for the upward diagonals. If this wrapping around is confusing to you, you can just write out the augmented matrix, and that will work for 3x3. But that is a really good question. What happens for these larger matrices? So I'm going to give you a much larger matrix, and we'll see what happens. So let's say I had 0, 1, 0, 1, 2, 1, 3, 2, 6, 5, 0, 3, 0, 0, 0, 2. How do we compute this ugly determinant? So this is a 4x4, and we now no longer have an easy way of doing it, and so we have to turn it into 3x3 matrices. Now, one of the things that you can use to guide yourself in deciding which row to expand along. So you can always expand along the top row, and that will work. But sometimes if you see a lot of zeros in some other row, it's easier to do it along a different row. And so here, note that there are 3 zeros down here. And if we look at the checkerboard pattern, that's plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. If we look at the checkerboard pattern, we can expand along the bottom row. And so what happens when we expand along the bottom row? Well, we get 0 times, the minor layer. So, sorry, this is negative 0, because that has a minus sign, but it doesn't really matter. So negative 0 times, you're getting rid of the first column and the bottom row. So this is going to be, let's see, did I do this correct? Hopefully I did this correct. 1, 0, 1, 1, 3, 2, and 5, 0, 3. It doesn't really matter, of course, because you have a 0 entry there. And then plus 0 times, well, this is the second column, and you're getting rid of the bottom row. So this is going to be 0, 0, 1, 2, 3, 2, and 6, 0, 3. Again, it doesn't matter because it's a zero entry, but let's try to do it correct. And please catch me if I make a mistake here. So this here is going to be the bottom row third entry. So we're subtracting those out. So this is going to be 0, 1, 1, 2, 1, 2, and 6, 5, 3. And this is going to be minus 2 times the cofactor expansion. So that's just 0, 1, 0, 2, 1, 3, and 6, 5, 0. Oh, it should be, yeah, yes, it should be a plus. Thank you, Jordan. Yep, that should be a plus. Okay, and note that I chose this to make life easy for myself because I chose this matrix to be the same as this matrix. And so, therefore, what you get is that this is equal to 2 times 18, which is equal to 36. Okay, so lattice cofactor expansions. I will not, unless the matrix has a super nice structure, which we'll see in a moment, I will not expect you to do anything bigger than 4x4. And if it's a 4x4, I will try to construct the problems so that they have relatively nice structure so that when you do the cofactor expansion, if you choose the right row or column, most of them will end up being 0. So that's something you should watch out for. For the cofactor expansion, do we have to do all the rows or just the top bottom to find the determinant? But it wasn't the same, then you would need to do the cofactor expansion again. Ah, yes. So here, I chose this to be yes. So I chose this to be easy because I had already done the cofactor expansion for this 3x3 matrix here. If we didn't already have the answer to that, yes, you would have to do the cofactor expansion again, or you'd have to use the wrapping around technique. For the cofactor expansion, do we have to do all the rows or just the top bottom to find the determinant? So that's the clever thing about cofactor expansion. You can do it along any row or any column. This is why I gave you the entire checker grid. You can choose any one row or any one column, and it'll get you the same answer. Proving that is a little bit harder, but you can prove that no matter which row or which column you choose, so long as you don't make an arithmetic error, you will get the same answer. If you do the wrapping technique for this 4x4 matrix, will you get the wrong answer? So for this 4x4 matrix, you might get the right answer. I haven't tried it for this 4x4 matrix, but in general, for 4x4 matrices, you will get the wrong answer. So you should not use the wrapping technique for a 4x4 matrix because very, very often you will get the wrong answer. That's actually a really nice exercise if you have a little bit of time and you want to play around. Try using the wrapping technique for a general 4x4 matrix, and try using the cofactor expansion for a general 4x4 matrix. The formulas will get really long and ugly, but you'll notice that there are a couple terms in the cofactor expansion that don't appear in the wrapping around diagonal technique. Okay, so now that we've done all that, let's try it out. Okay, so I want you to get the determinant of this matrix. And let's go ahead and reset this. So remember, you can either use the cofactor technique or you can use the wrapping around technique for this particular matrix. I'll give you all a moment to decide what the answer is. So let me go ahead and write out the cofactor expansion, though you'll still need to compute it. So this is equal to 1 times 5, 6, 8, 9 minus 2 times 4, 6, 7, 9 plus 3 times 4, 5, 7, 8. Oh, okay. So it looks like nice. Oh, wait, we got a pi in there? Interesting. Yeah, so it looks like everyone got B. So let's go ahead and write this out just so that everyone's on the same page. So when we write this out, this is equal to, well, 1 times 45 minus 48 minus 2 times 36 minus 42 plus 3 times 32 minus 35. And this will end up being equal to minus 3 plus 12 minus 9, which is equal to 0. And so the answer is B. Now, was there any other way to see that the determinant is equal to 0? Well, remember that the determinant equal to 0 means that it's not invertible. So, for example, if I told you this, if I told you that 1, 2, 3, 4, 5, 6, 7, 8, 9, if I gave you this vector, 1 minus 2, 1, you'll find that that is equal to 0, 0, 0. And so therefore, this is not invertible. Remember that a matrix is not invertible if it sends a non-zero vector to 0. So that implies not invertible. So if you happen to know that this matrix had a vector that it sends to 0, then you would know that the determinant is equal to 0. But now that we know the determinant, we automatically know that's not invertible, even if we don't know that there's this vector that it sends to 0. Because the determinant is equal to 0, you know there must be some vector, even if you don't know what vector that is. Okay, so let's try one that's a little bit more fun. So these kinds of things will show up relatively often. I'm going to ask you to find the determinant of this 5 by 5 matrix. So now, note that I haven't explicitly taught you how to do a 5 by 5 matrix, but I gave you this general formula for figuring out the determinant using a cofactor expansion. And note that this matrix is very nice. It's completely diagonal. So what actually is the determinant here? So now, if you're clever, you might notice that the determinant also corresponds to a volume scaling, and here we're scaling all the axes by 2. So what would the volume be, the hypervolume of a 5 cube be, if you were scaling everything by 2? Okay, it looks like we're starting to get some replies. Okay, so it looks like we have a lot of D's, and yes, that is correct. And there are several different ways to see this. One of them is the hypervolume thing that by hypervolume, so you have area is 2-dimensional, you have volume, which is 3-dimensional, and you have analogs in higher dimensional space. We're not going to go into it in too much detail. It's just a way of thinking about it if you're familiar with that kind of terminology. But it doesn't actually matter. You don't have to know that because we have a formula for the determinant. And, and it turns out you can do this relatively easily by just doing a cofactor expansion. So this is equal to, well, let's expand along the top row. Well, you know the top row only has one entry that's non-zero. So that turns out to be 2 times the determinant of 2, 2, 2, 2 with zeros everywhere else. By this notation, sorry, let me not use that notation. You'll see this notation a lot more in your later classes probably, but let me actually explicitly write all the zeros. Minus 0 times something, plus 0 times something, etc. But those all don't matter, right? Because you know that you have 0 times everything if you expand along the top row. Okay? And now we can do the same thing. So if we expand along the top row again, so that's 2 times 2 times the integral of 2, 2, 2, 0, 0, 0, 0, 0, 0, where we've expanded along the top row again. And we can continually do this, and so this is equal to 2 times 2 times 2 times 2 times 2, which is equal to 32. And for some reason, I have a couple random red marks. Okay, and it turns out that this is a general fact about diagonal matrices. The determinant of a diagonal matrix, where everything's along the top diagonal, is just the multiplying together all the values along the diagonal. And there's a really good reason for this if you think about this geometrically, which is that a diagonal matrices scales something called the standard basis. So, erase that. So, if you think about a matrix that's diagonal with entries 1, 2, and 3, what it's doing is it's scaling each of your coordinates. You're scaling your x coordinate by 1, scaling your y coordinate by 2, and your z coordinate by 3. So another way of thinking about this is through something called basis vectors, which are going to play a role later when we talk about eigenvectors. So if we think about these basis vectors, we have E1, which is, we're going to just be, it's going to be 1, 0, 0. And then let's have E2, which is equal to 0, 1, 0, and E3, which is equal to 0, 0, 1. So these are called your standard basis. And you'll note that when you have AE1, that's equal to 1, 0, 0, 0, 2, 0, 0, 0, 3 times 1, 0, 0. That's equal to just 1, 0, 0, which is equal to E1. And similarly, AE2 turns out to be equal to 2E2, and AE3 is equal to 3E3. And we can, let me give you the punchline first. So if you have a diagonal matrix with entries, we're going to call them lambda 1 through lambda n, because that's just standard math notation. The standard basis vectors, where E1 through En is a vector with zeros everywhere except a 1 in position I, then it scales it by AEI is equal to lambda I EI. Can you explain the AE2 part again a little bit slower? Yeah, so let's write out AE2. So AE2 is 1, 0, 0, 0, 2, 0, 0, 0, 3. E2 is 0, 1, 0. When you multiply this out, the top row and the column, you end up getting a 0. The second row and the column vector, you end up getting a 2. And the third row and the column, you end up getting a 0. So what's happening is that, let me draw this geometrically. So if we draw this geometrically, we're in 3 space, right? So this is x, this is, let's call this one y, and let's call this one z. And what we're doing is we're starting out with these unit vectors. So this one here is 1, 0, 0. This one here is 0, 1, 0. And this one here is 0, 0, 1. Okay, so we have these 3 different vectors in 3 space, and these are the basis vectors since they measure sort of the different directions that you're going along. And then what happens when you apply A to it? Well, when you apply A to this, well, AE1 is still equal to 1, 0, 0. So you still get the same thing. When you apply to the second vector, you double the length. And so that gives you A times 0, 1, 0 is equal to 0, 2, 0. And when you have in the third column, in the z-axis, you're actually tripling it. So this here is going to be A times 0, 0, 1 is equal to 0, 0, 3. So basically, when you have this diagonal matrix, it's scaling your figure, whatever it is in 3 space, along each of the different axes. So this is leaving your x-axis unchanged. It's doubling the size of anything, any direction along the y-axis, and tripling the size of anything along the z-axis. Okay, so this is what a diagonal matrix does, and this is why diagonal matrices are relatively easy to understand. You can also sort of understand the determinant of this matrix is going to be 6, because you're just multiplying the entries together along diagonal, because that's what you're scaling the volume of a unit cube by, because you're scaling one side by 1, one side by 2, and one side by 3. Okay, so now what about non-diagonal matrices? So for diagonal matrices, you can basically think of it as just operating independently on each of the different standard axes. But for a non-diagonal matrix, let's say we have this 1, 1, 1, 1 matrix. What's it doing? Well, it's sending an xy coordinate to x plus y and x plus y. So let's see a couple examples of where this sends stuff. So if you have some original vector here, let's say this is the vector 1, 0, and let's say this here is the vector 0, 1. Turns out both of these get sent to the vector 1, 1. Right? So if you start with the 0, 1 vector, you multiply by the matrix 1, 1, 1, 1, you end up getting 1, 1. So that doesn't seem to be a scaling behavior, right? So we have A01 is equal to A10 is equal to 1, 1. So this does not scale, doesn't scale these two vectors. Does not scale 0, 1 or 1, 0. Okay, but what if we choose a different vector? So let's say that we chose another vector. What if we happen to choose the vector 1, 1? Well, when you plug in 1, 1, so then let's see, A times 1, 1 is equal to 1, 1, 1, 1 times 1, 1, which is equal to 2, 2, which is equal to 2 times 1, 1. So what you're doing is you're scaling this by a factor of 2. So that's going to end up giving you the point 2, 2. So A scales the vector 1, 1 by a factor of 2. And now it turns out there is another vector that we can also show a scaling behavior for. So let me draw this out a little bit differently. So let's suppose that our starting vector was this one here. So this is 1 minus 1. Well, it turns out that when you multiply A times 1 minus 1, you end up getting 0, 0, which is equal to 0 times 1 minus 1. And so therefore, this thing scales 1 minus 1 by a factor of 0. So it's multiplying it by 0, and you end up getting this point here. Okay, so you see, even when you're working with a non-diagonal matrix, you're no longer scaling the normal vector, the standard basis of just the axes, but you're scaling some other vectors. And that's one of the important properties of, matrices in general, is that often you can break down the behavior of a matrix into what it scales up and what it scales down. So this brings us to our discussion of eigenvalues and eigenvectors, which is precisely formalizing this idea of scaling particular important vectors. So let A be an n by n square matrix. N by n square matrix, and let V be a non-zero vector of length n. Note that any zero vector, when you multiply A by a zero vector, you always get 0. So that's not particularly important. What would the first... let me finish this definition, and I'll answer your question, Sam. So let if AV is equal to lambda V, for some number lambda, then V is an eigenvector of A with corresponding eigenvalue lambda. Together, you sometimes call these an eigenpair, lambda and V. In slightly less formal words, an eigenvector V is a vector that gets scaled by a constant multiple lambda when multiplied by A. And if V is and note that if V is an eigenvector for the eigenvalue lambda, then so is kV for any k not equal to 0. So if you go back to that original matrix, so we had 1, 1, 1, 1, there are two eigenpairs. Has two eigenpairs. And those would be 2, and this is 1, 1, and 0, 1, minus 1. So the matrix 1, 1, 1, 1 scales the vector 1, 1 by a factor of 2. So if you start with 1, 1, you get multiplied by 2, and you get 2, 2. But if you have a vector 1, minus 1, that gets scaled by a factor of 0, and so it gets sent to 0. Note that, of course, we can also write out different eigenpairs. So we can also write out 2, 2, 2. Because you're just scaling by a constant multiple, and you're not changing the vector at all. You're not rotating the vector at all. I mean, at least not yet. And so therefore, if 1, 1 is an eigenvector, so is 2, 2. Similarly, if 1, minus 1 is an eigenvector of 0, and so is minus 1, 1. And you can multiply these out, and you see that it has the same scaling behavior. Okay. Let's go on. Oh, I have a typo on my next slide. Well, we'll see what people respond. So, let's suppose we have a vector like this. Which of the following are eigenvectors of A? Oh, yeah. Let me go back to the previous slide while and answer this question. So, also works 2 and minus 2, 2. Minus 2, minus 2. That is also an eigenvector. Or something like 0, minus 2, positive 2. Okay, but let's see what are which of the following are eigenvectors. And I should warn you, I made a typo in this problem, so I apologize. So there are actually 2 correct answers to this problem. I'll just go ahead and tell you that in advance. Mostly because I made a mistake. But so what I'm asking is, which of the following are eigenvectors of A? Now, recall that an eigenvector just means that it scales the original thing. So, okay, so we have a couple of replies. We have some C's. A bunch of C's, actually. Okay. So, now let me go ahead and tell you now, there is another eigenvector here. What is the other eigenvector? Yep, looks like Jordan also got B is also an eigenvector. So let's actually look through this and work through it carefully, just so we understand what are eigenvectors. So we have our original matrix: minus 9, 6, 20, 2, 2, minus 4, minus 6, 3, 13. And so now let's take a look to see if A is an eigenvector. So we think it isn't, but let's take a look and see what happens. So, oh, that's a positive 2. So 2 minus 6 and 5. So this is going to be equal to minus 18 minus 36 plus 100, and 4 minus 12 minus 20 minus 12 minus 18 plus 65. We add these all together, you get 46 here, minus 28, and 35. So this is not an eigenvector. And, well, let's see what happens when we do B. Minus 9, 6, 20, 2, 2, minus 4, minus 6, 3, 13. And let's say 6, 1, 3. So this is going to be equal to minus 54 plus 6 plus 60, 12 plus 2 minus 12, and minus 36 plus 3 plus 39. And when you multiply that out, it turns out it's going to be 12, 2, and 6, which is equal to 2 times 6, 1, 3. So therefore, B is an eigenvector. And note that C is also an eigenvector, because this is equal, so C also eigenvector. Is this the only way of testing it to multiply it out? You'll have to multiply something out to test if. So for B, 2 would be the eigenvector. Yes, for both B and C, actually. So for both B and C, 2 would be the eigenvalue of that eigenvector, because you're scaling it by 2. And then if you plug in C again, you'll also see that it doubles it. This is not the only way of testing it. You can also solve it without so here I gave you the answer, and you're basically checking the answer by doing matrix multiplication. If you don't know the eigenvector to begin with, well, that makes things a little bit harder, because then you have to solve for it, and that involves a Gaussian elimination, or solving a system of equations. So that will be, well, the next part of the lecture. So let's go ahead and talk about how do we find eigenvalues and eigenvectors. So here, what I've done is I've just given you a couple things. I've asked you, is it an eigenvalue or eigenvector? And in the next part, we're going to talk about how do you find them if you don't know to begin with. And there's a very important theorem that connects together the eigenvalues of a matrix with the determinant of a related matrix. So if you have an m by n matrix, if lambda, some real number lambda is an eigenvalue of A, then the determinant of A minus lambda I is equal to 0. I'm going to give you this proof because I think it's important to understand what's going on. You will not be expected to know this proof. So if you want, you could tune out a little bit, but if you want to try to understand what's going on, you should listen. So the proof here is that the definition of an eigenvalue is AV is equal to lambda V for some non-zero V, vector V. So if we subtract out, this is AV minus lambda V is equal to 0. Note that you can rewrite this as AV minus lambda I times V is equal to 0. And this is, of course, because V is equal to IV, since anything you can multiply by the identity matrix. Then you can use the distributive property, A minus lambda I times V is equal to 0. So this is the distributive property of matrix multiplication. And therefore, we know that A minus lambda I is a singular non-invertible matrix because V is not equal to 0, and this matrix sends V to 0. Since this A minus lambda I is some other matrix, which then implies that the determinant of A minus lambda I is equal to 0. So let's use this theorem to find the eigenvalues of the example we showed earlier. So we had A is equal to 1, 1, 1, 1, and we knew that lambda 1 is equal to 2 and lambda 2 is equal to 0. But now let's suppose we don't know that to begin with. So we don't know that. What do we do? Well, what you can do is you can take the determinant of A minus lambda I, which is equal to the determinant of 1, 1, 1, 1 minus lambda times the identity matrix, which is 1, 0, 0, 1. This is equal to the determinant of 1, 1, 1, 1 minus lambda 0, 0, lambda, which is equal to the determinant of the matrix 1 minus lambda, 1, 1, 1 minus lambda. And we know how to take this determinant because you just take the top diagonal minus the other diagonal. So this is equal to 1 minus lambda squared minus 1. So note that here we're taking a determinant where we have a variable inside. So we don't know this value of lambda, but we know that it's some number, and we're going to still take the determinant and just work through it with this unknown. So when you do this, you get 1 minus 2 lambda, 1 minus 2 lambda plus lambda squared minus 1 is equal to, and what do we know that this thing is equal to 0, because we're assuming that lambda is some eigenvalue. And so then we know that lambda squared minus 2 lambda is equal to 0, or if you factor that out, lambda times lambda minus 2 is equal to 0, which implies that lambda is equal to 0, or lambda is equal to 2. Okay, so that is so if you're given a matrix, you can always solve for the eigenvalues by solving for the determinant of the A minus lambda I. So you may hear something called a characteristic polynomial. That is this determinant of A minus lambda I. We're not going to talk about it too much in this course, but you might hear that if you see linear algebra in any of your future courses. I'm just going to mention that. But basically what you have to do is you just have to solve for a determinant of A minus lambda I is equal to 0, and that gives you all the values of lambda that are eigenvalues. So let's go ahead and try this out. So I have two matrices here. Let's just do the first one first. And I'm going to reset. So is the determinant is always 0 for A minus lambda I. So to answer Sam's question, you always set the determinant of A minus lambda I equal to 0 when you want to solve for an eigenvalue lambda. So if it's an eigenvalue, then the determinant will be equal to 0. If it's not an eigenvalue, then it won't. But the whole point of this procedure is to solve for the eigenvalues. Why did my reset not work? Come on. My thing break? Okay, there, that worked. Okay, so it looks like we have a couple replies going in. So it looks like everyone's guessing A, and this is correct. So let's work this out. So this is going to be 1 minus lambda, 2, 0, 1 minus lambda. Because I'm sort of combining together steps of A minus lambda I. You just have to subtract lambda from every entry along the diagonal. Well, this is equal to 1 minus lambda squared minus 2 times 0. So that's equal to 0. And this thing gets canceled out. So therefore, lambda is equal to 1. Okay, let me reset again. And let's see, what do you think are the eigenvalues of this matrix? So this 1, 2, 3, 4 matrix. Okay, looks like we have one vote for A. Let's see. Well, let me go ahead and write out the general procedure. So you need to take the determinant of 1 minus lambda, 2, 3, and 4 minus lambda. And you need to set this equal to 0. Okay, it looks like we have a mix of responses. So let's see what happens. Oh, sorry, this is still updating. Okay, so it looks like A and E are our two responses. So let's see what happens. So we want to set this determinant equal to 0. And so that means that this is equal to, so we have 1 minus lambda times 4 minus lambda minus 6 is equal to 0. When we write this out, you get lambda squared minus 5 lambda plus 4 minus 6 is equal to 0. Lambda squared minus 5 lambda minus 2 is equal to 0. You can use the quadratic formula. So you get lambda is equal to 5 plus or minus the square root of b squared. So that's 25 minus 4ac. So that's plus 8 over 2. So lambda is going to be equal to 1/2 times 5 plus or minus the square root of 33. So you can write these out. You can assign them arbitrarily, lambda 1 and lambda 2. So that's just a labeling. So lambda 1 is equal to 5/2 plus square root of 33 over 2, and lambda 2 is equal to 5/2 minus the square root of 33 over 2. And so the correct response is actually E, none of the above. We do have two eigenvalues, but I didn't give you those as options here. I think this might be one of the few times that none of the above has been the correct answer. So let's try it out again. So there's a trick to this one, but oh, sorry. Yeah. So find the eigenvalues. Yeah, just a moment. Let me go back a quick second. So basically, in order to solve for the different eigenvalues, you just set the determinant of a minus lambda I equal to 0, and then you solve for lambda as an unknown variable. And here we were just using the quadratic formula after we had expanded it out. Yep. Okay, so now let's get back to this question. I want you to find the eigenvalues of this matrix. So note that this is a very special matrix, right? So this is a diagonal matrix. So what do you all think are the eigenvalues here? Okay, so let's see. We are starting to get some responses. Looks like we have a lot of D's in chat. So that is correct. All three of these are eigenvalues. And there are a couple ways to think about this. One is, I told you earlier that a diagonal matrix, it scales each of the individual standard basis elements already. And so a diagonal matrix, you can just know from that fact that because it's scaling each of the individual standard basis vectors, the eigenvalues are just on the diagonal. We can also verify this using our Euler formula. So determinant of a minus lambda I is going to be equal to the determinant of 1 minus lambda 0, 0, 0, 2 minus lambda 0, 0, 0, 3 minus lambda. So that's equal to, well, let's go ahead and do it using cofactor expansion. Why not? So that's equal to 1 minus lambda times 2 minus lambda 0, 0, 3 minus lambda, which is equal to 1 minus lambda, 2 minus lambda, 3 minus lambda is equal to 0, which implies that lambda is equal to 1, 2, or 3. So we have 3 eigenvalues here. And this turns out to be a general fact about not just diagonal matrices, but any triangular matrices. So triangular matrices always have their eigenvalues on the diagonal. This is one of the reasons that we really like triangular matrices, because you can just look at it and you immediately know the eigenvalues. Another nice fact is, if you look at a triangular matrix, you can also immediately figure out the determinant just by multiplying together the entries along the diagonal. And this is actually one of the subtle and deep facts about determinants, which I'm just going to allude to and not prove. But you'll notice that if you go back on the previous slide, on the very first example, we also had a triangular matrix, and yes, the diagonals were indeed on the diagonal. Oh, what's the difference between diagonal and triangular? Yes, so, let's see. If you have entries along just the diagonal, then this is diagonal. If you have entries there, so if you have entries along the diagonal and above it, that is triangular. Or you can also have triangular the other way. It's also triangular. So diagonal means the entries are, the only non-zero entries are on the diagonal. Can it be diagonal the other way? That is a very good question. No. That actually fails in, so this, we do not call this a diagonal matrix. Not diagonal. So it cannot be diagonal the other way, and it also can't be triangular the other way. Not triangular. So when I refer to, so matrices have a preferred orientation, and that's from the top left down to the bottom right. This is just the artifact of the way that we write it. And so when you refer to a diagonal or a triangular matrix, you mean that you're talking about the, well, if you're thinking about the triangle as a right triangle, the hypotenuse, or the diagonal being from the top left to the bottom, right. And that is actually very important. So thank you very much for that question. So triangular matrices have eigenvalues in their diagonal, and when we refer to triangles, we only refer to ones where they're above or below the main diagonal. In fact, in linear algebra, we almost never talk about the other diagonal. That just doesn't exist for us. Okay. Oh, I still have a couple more slides, and then we'll have our break. So let's take some time to find the eigenvectors of a matrix. So let's go ahead, and I'm going to give you a matrix. Let's say A is equal, oh, sorry, we're going to do this one together. A is equal to 0, 1, 1, 0. So this is a good example. This is not a diagonal matrix. And we'll see this when we look at the eigenvalues. So you get minus lambda, 1, 1, minus lambda are the, this is A minus lambda I. Take this determinant, you get lambda squared minus 1 is equal to 0. You can factor that out, lambda plus 1, lambda minus 1 is equal to 0, and lambda is going to be equal to 1 and minus 1. So we can go ahead and label lambda 1 is equal to 1 and lambda 2 is equal to minus 1. So note that these eigenvalues were not found on the diagonal. So this is a very good counterexample to the idea that the other diagonal matters. The other diagonal is basically meaningless. Okay, so let's start with lambda 1 is equal to 1. Well, then what do we have? Then we have, what we want is 0, 1, 1, 0 times xy to be equal to, well, what do we want? We want to multiply it by 1. So that should just be xy again, right? Another way of rewriting this is we can rewrite this as, come on. We can rewrite this by subtracting xy from both sides, and you get minus 1, 1, 1, minus 1. So if you look, this is precisely the matrix that we were taking the determinant of, times xy is equal to 0, 0. And we can solve this using Gaussian elimination. So minus 1, 1, 1, minus 1, 0, 0. And when we do Gaussian elimination, you'll find that these you end up with 1, minus 1, 0, 0, 0, 0. So Gaussian elimination. So now what does this mean? When we convert it back into vector form, so this means that x minus y is equal to 0, and so y is equal to x. And you can conclude that eigenvectors, v1, are of the form x, x. So one particular eigenvector is 1, 1, but it turns out that 2, 2 is also an eigenvector. So you can see when you're solving for these eigenvectors that there will always be a free variable, because you can scale things and you still get an eigenvector. Let's do it for lambda 2 is equal to minus 1. So we do the same thing, and it turns out that we'll end up with 1, 1, 1, 1, 0, 0 will be our augmented matrix. And when we do a Gaussian elimination, that's just going to be 1, 1, 0, 0, 0, 0. Oh, yes, let me explain it slower. Let me start over and explain that entire thing slower. So the whole point of an eigenvalue is that it scales, when you multiply by the original matrix, it scales everything, right? So 0, 1, 1, 0 times xy, we want to scale it by a negative, right? So this is equal to minus x minus y, in order to solve for an eigenvector corresponding to the eigenvalue minus 1. So now what we can do is, if you think about this, this is precisely going to be the, let me write it out in system of equation form. So this is also meaning that y is equal to minus x and x is equal to minus y. Okay? Just by multiplying out the two different entries of this matrix. So now, one way to look at this is to take this and turn it back into a system of equations. X plus y is equal to 0, x plus y is equal to 0. And so that turns into the system one, 1, 1, 1, 0, 0. Okay? But you don't have to do it that way. You can also just directly use x is equal to minus y, y is equal to minus x, and you get v2 is going to be equal to x and minus x. So this gives you 1 minus 1 as one of your eigenvectors. Okay, so basically all we're doing is we're solving for an arbitrary vector xy that has this correct scaling behavior. So by using the determinant of a minus lambda I, we could get the, we could figure out what the eigenvalues are. And so that gives us the what the scaling behavior is, and then we have to look to find a vector that it does that to. So what vector does a keep the same? And so that was this part over here on the left. And then we had what vector does the a flip? And so that's this part here on the right. And then you just have to solve for that system of equations. Let's do another example. So let's do another example. This one's going to be a is equal to 1, 2, 3, 4, 5, 6, 0, 0, 0. Since this, yeah. So let me try with this other example and see if that makes things a little bit more clear. Okay. So we have lambda 1 is equal to 1. We have lambda 2 is equal to 2, and we have lambda 3 is equal to 3. Right? Because this is a triangular matrix, and so we know the eigenvalues are just on the diagonal, which makes life easier. So let's start by considering the case where lambda 1 is equal to 1. Okay? So because lambda 1 is equal to 1, we know that a times some vector v, we don't know what this vector is, but a times some vector v, v1, which is going to correspond to the eigenvector for lambda 1, is going to be lambda 1 v1. Okay? Where v1 is some vector x, y, z. And what we want to do is we want to solve for v1. So how do we solve for v1? Well, in order to solve for v1, we can just plug it into this system of equations. So we had 1, 4, 6, 0, 2, 5, 0, 0, 3 times x, y, z is equal to lambda 1, which is 1, times v1. So that's x, y, z. Okay? So now, there are a couple of different ways of rewriting this. And one way to rewrite this is to note that this is equal to, one way to rewrite this is you can rewrite this as the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 times x, y, z. Okay? And then you can subtract both sides and then use the distributive property. And so this ends up giving you the matrix 0, 4, 6, 0, 1, 5, 0, 0, 2 times x, y, z is equal to the 0 vector, 0, 0, 0. Okay? Now, once we've done that, what we can do is we can write this as an augmented matrix, 0, 4, 6, 0, 0, 0, 0, 1, 5, 0, 0, 2. Why is the equal to the 0 vector? Because we've subtracted out by the same thing on both sides. So let me write this up here. So we have AV1 is equal to lambda 1 V1. So that means that what we wrote is AV1 is equal to lambda 1 IV1, right? And so then we can move it over to the side. So we have A minus AV1 minus lambda 1 IV1 is equal to 0, where 0 is a 0 vector. And then what we do is we combine together the A minus lambda 1 I V1 is equal to the 0 vector, and that is precisely that there. So we've subtracted all the entries on the diagonal by 1 because these are basically doing these equations, and we're subtracting out by the identity matrix on both sides. The identity matrix times lambda 1. Does that clear things up a little bit more? Okay, so now we have the system of equations, we just need to solve for them. So we need to solve for the system of equations, but this is just Gaussian elimination, right? So the first step of Gaussian elimination is we're going to divide the first row. So let's say row 1 is row 1 divided by 4. And let's say row 3 is equal to row 3 divided by 2. So then you get 0, 1, and let's see, this is 3 halves, 0, 1, 5, 0, 0, 1, 0, 0, 0. But now, of course, we can just subtract out, and so we can have row 1 is equal to row 1 minus 3 halves row 3, and row 2 is equal to row 2 minus 5 row 3. And you're left with 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. And of course, the second vector doesn't really matter. So this gives you 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, by just rearranging the vectors and combining them. And so this implies that x is equal to 0 and y is equal to 0 when you put it back into equation form, and there's no constraint on z. So v1 is equal to 0, 0, z, which gives you 0, 0, 1 as an eigenvector, or 0, 0, minus 1. Okay, let's do that again for the second eigenvalue and try to make things a little bit more clear. So let's try it again. So note that we had our original matrix, which was 1, 2, 3, 4, 5, 6, 0, 0, 0. And we had lambda 2 is equal to 2. So then what we want is we want this times x, y, z is equal to 2x, 2y, 2z. Now, I'm going to do this one a little bit differently than the last one. because all we're doing is we're solving a system of equations. So all we're doing is we're saying that when we multiply this out, x plus 4y plus 6z is equal to 2x, and 2y plus 5z is equal to 2y, and 3z is equal to 2z. This is entirely equivalent to the other system, and all we have to do is we have to solve these things, solve this, right? So the first thing you'll notice is that this implies that z is equal to 0. So if z is equal to 0, then the entire thing is just x plus 4y is equal to 2x, and 2y is equal to 2y, and z is equal to 0. But now, 2y is equal to 2y, well, that doesn't mean anything, so that's not really a constraint. And then this turns into x is equal to 4y. So you end up with a set of constraints, x is equal to 4y, and z is equal to 0. So therefore, v2 is equal to, well, 4y, y, and 0. Which implies that one eigenvector is 4, 1, 0. Or you could have another eigenvector, which is minus 4, minus 1, 0. And that would also be an eigenvector. Okay, does that sort of make sense? All we're doing is we're solving the system of equations. And in the previous slide, we did it by converting it into this augmented matrix and then doing row operations. Here, we did it using substitution, just solving a system of equations. Either way works. All you're doing is you're just trying to solve for x, y, and z. And what ends up happening is at the end, you end up with one free variable. Sometimes it's x, sometimes it's y, sometimes it's z, and you just have to plug in some value for that free variable, and that gives you the eigenvectors. Are those the only two eigenvectors? Or 8, 2, 0. So these are all any multiple of this, because you're plugging in y is equal to 1, or y is equal to minus 1, or y is equal to 2. Those are all eigenvectors corresponding to lambda 2 is equal to 2, but they're not linearly independent because you can multiply one to get the others. Okay? So this is these are the family of eigenvectors corresponding to lambda 2 is equal to 2. Okay. Yes, 16, 4, and 0 is also an eigenvector. Yep. Okay, so I will go ahead and have you guys try it out now. So I want you to compute the final eigenvalue for lambda 3 is equal to 3. So what is the eigenvector corresponding to that? And I will take this time to go ahead and give you your break. Sorry it's a little bit late, but yeah, so I'm going to leave off this half of lecture with this problem, and let's go ahead and take a 10-minute break and come back at 1:35. And then we may not end up getting to all material today, but that's all right. In the next third of lecture, I'm going to be talking about some interpretations, some biological interpretations of eigenvalues and eigenvectors. So with that, I will end the recording, but I'll give you some time to work this out and try to figure out what the corresponding eigenvector is.